we are going to find the slope of this line instead of using 2 points that are 1 unit apart, using points that are an arbitrary number of units apart, or thought of another way, picking any 2 points on the line. And the way we're going to be able to do this is using similar triangles. So as a reminder, we said slope represents the amount of increase in y values at the point 1 unit to the right of a point I fixed. This is a line we looked at last time, and we actually determined that the slope of this line was 1 5/10, or 3/2. And we determined that because we identified that the length of this little segment in here, that purple segment, was 1 1/2, 1 5/10, when we moved over 1 unit. So we had this little triangle we've drawn. We call this a slope triangle. Slope triangles get their names because the ratio of the height divided by the base will always be equal to the slope. And they're always right triangles. We also can call this computation rise over run. So we're going to use rise over run to mean the change in y versus the change in x. So I'm going to change my selection for my points Q and R. I'm going to pick a second point R on this line that's way up here. I'll let that be my R. And while we know its coordinates, for the sake of argument, we're going to write this as point P1, P2, and R as having coordinates R1, R2. And that's so that we can see how this works in general. Now I can draw another slope triangle. The first thing I want you to notice is that these are similar triangles. I'm going to name the other 2 points A and B. And so I want to point out that triangle PAB is similar to triangle PRQ. How do I know they're similar? Look at the picture for a second. I'm thinking to myself, and I see a number of parallel lines. I notice that the line that includes the segment AB is parallel to the line through RQ. Oh, I forgot to label Q. And I know that because they're both vertical lines. Therefore, have that the angles formed when they hit the horizontal line that goes from P to Q will be the same. So I know that I have 2 right angles. So that's one angle in common. Secondly, I notice that they share a common angle. There's actually one angle that is part of both triangles. Do you see it? Type it in the chat. That's right. The angle at P formed by the line and that horizontal line is common to both triangles right here. So they're similar by angle because they share 2 angles that I can see for sure in both cases. Now that we have 2 similar triangles, I can build some ratios to relate them. So I knew that slope was this measurement of the length of AB, because AB is the amount I've moved up when I go over that 1 unit from P to B. And therefore it's AB divided by 1, or the length of AB divided by the length of PB. So that's the initial ratio. I also know that my bigger triangle, triangle PRQ, has the same ratio of base to side. That equal to the length of RQ divided by the length of QP, or PQ. Now, let's figure out how we could find both of those lengths, because I know AB and PB is just the number M. So what is RQ divided by QP? There's a vertical number line that goes from R to Q. And remember, Q has the same Y coordinate as P. So whatever Q is, its Y coordinate, its X coordinate matches R, but its Y coordinate matches P. So I'm going from a point R1 comma R2. That's where I've ended up, and I've moved there from P2. How could I describe that difference? Well, I've done R2 minus P2. The absolute value of that should be the length of the segment RQ. And in my image, because we've moved upward, this should be a positive quantity. In the other direction, when we go horizontally, well, now we're doing the base PQ. How far is that? Well, that's 2 points, both at the same height, but they have different x coordinates. The distance in this direction, I should be able to take the rightmost point, which is at Q, and subtract the x coordinate of the leftmost point. So Q's x coordinate is R1, subtract P1. That's RQ over QP. And so I get this formula. I want to show it to you now in the context of this example. So we're actually going to use the numbers that we see, and I think it'll make it simpler. In our example, we're going to find the slope, which we're also going to call the rate of change. And we're going to use points using P and R. So I'm going to erase some of the other stuff that's in the way. Remember, we know what the slope should be. We had already found the slope in this example. Well, in our example, what are the coordinates for R and Q? Well, R is 1, 2 units to the right of the y-axis. So R's coordinates are 2, comma, how many up is it? Looks like its y-coordinate is 5. And Q has coordinates 2 in the x as well. It's on the same vertical line, but its y is 1 unit below. Oh, that's a -1. I have the coordinates of my 3 points. So if I use my formula, I want to have the vertical change. So I'm going from a point that's up on the number line at height 5, up here, and I'm going to subtract off the height that I'm at the bottom. So 5 minus -1 divided by, now we've got our x's, 2 minus -2. And so what's our change? 6 in the numerator and 4 in the denominator. That's equivalent to 3/2, which is the slope we found before.